Stuck on in waiting endless nights to get a call. Hung up on you. I wonder, do you ever think of me too?
In this video, you will define and understand function, domain, codomain, and range. Using the conditions in the definition of function, you will identify if a set of ordered pairs is a function. And if a set of ordered pairs is a function, you will classify it as an injective or surjective or bijective. Let's start this video by recalling the formal definition of a function we have learned from our class. Let A and B be sets. A function from A to B, denoted by f is a function from A to B, is a relation from A to B such that for every A element of A, there exists a unique B element of B such that quantity A comma B is an element of the function. We have learned that in mathematics, mathematical concepts or terminologies are defined by conditions. Hence, to understand the definition of function, we need to understand the conditions written in its definition. First, when we deal with a function, we deal with sets. Second, a function is said to be a relation or binary relation. Third, we need to understand what do we mean by the quantifier for every A element of A. Also, the quantifier, there exists a unique B element of B. More importantly, what do we mean when we say unique? So here are the terms we need to unlock so that it will be easy for us to understand a function. We know that a set is a well-defined collection of distinct objects. We use this symbol called set to refer to a collection of distinct objects. When we say distinct, we mean that every element is unique from one another. Therefore, when we place each element in the set, we need to make sure that no element is repeated. We have learned that there exists a relation or binary relation between subsets or elements of A and B, or we say an element A is related to an element B if and only if the ordered pair quantity A comma B belongs to the set. Did you know that the universal quantifier for every or for each in mathematics means all? Therefore, when we say for every A element of A, we mean that all elements in set A, no one is excluded. In this video, we refer to A as the domain of the function. In other words, it is the set of inputs or x value, while small letter a represents each x value or input we can find in our domain. Just to let you know, the symbol for every or for each is this. It looks like an inverted capital A, right? Did you know that the existential quantifier there exists in mathematics means there is at least one? This would mean that the minimum value is 1 and the maximum value is infinity. However, because of the word unique, which means one and only one, therefore, in the definition of a function, the maximum value we are talking about is 1. Putting all this together, for every A element of A, there exists a unique B element of B, means that Each element we can find in set A or our domain must be paired up to one and only one element in set B. The set B is what we call the codomain or set of possible outputs or Y values, while the small letter b represents every output or Y value in the codomain. Just a nice to know, we use this symbol to denote there exists a capital E facing to the left. To sum it up, in a function, if A and B are both sets, then the element of each set must be unique or there is no repetition of an element in a set. In a function, if A and B has binary relation, the ordered pair quantity A, B must belongs to a set. In a function, every element A of domain or set A must be mapped to one and only one element B of codomain or set B. Let's try the example 1. It says here that we need to determine if the set of ordered pairs M equals set of quantity 1, 2, quantity 2, 3, quantity 3, 4, quantity 4, 5, ellipsis is a function. We were asked to use the arrow diagram. From the given set of ordered pairs, I know that the elements of the domain M are the first value in each ordered pair. Thus, the elements of the domain M are 1, 2, 3, 4, ellipsis. I also know that the second value in each ordered pair is the range or codomain. Therefore, the elements of the range are 2, 3, 4, 5, ellipsis. I know. At this point, you are interested to know the difference between codomain and range, right? The codomain is set of possible outputs, while the range is set of outputs. For instance, we are given a function. It says that its set of possible outputs or codomain is the real numbers system. But after plugging in every given x value to the function, we only get counting numbers as outputs or range. This example shows what we meant when we say codomain is a set of possible outputs and range is a set of outputs. However, just like here in our example, there are times that the range is also the codomain. This happens when all possible outputs become the Y values. Now, to know if set M is a function, we will use the arrow diagram. I will create an ellipse that represents the domain M. Some books refer to this as the pre-image. Now, I will put each element of the domain M inside this ellipse. I will make another ellipse for the range M. If domain is pre-image, range M is the image. Similar to what we did in the first ellipse, I will put each element of range M inside its ellipse. Now, the arrow diagram means that we need to map every input in every ordered pair in set M to its output. Hence, input 1 is mapped to output 2, input 2 is mapped to output 3, input 3 is mapped to output 4, and input 4 is mapped to output 5. We will use the arrow diagram to make a conclusion about set M, if it is a function. Let's check. The first condition is met because every element in domain M and range M is unique. Also, the second condition is met because every ordered pair belongs to set M. Lastly, all elements in domain M were mapped to one and only one element in range M. Since all conditions in the definition of a function are met, set M is a function. Let's have another example. Here, we will determine if set I is a function. We saw that the ordered pairs of set I are quantity 1, 0, quantity 0, 1, quantity negative 1, 0, and quantity 0, negative 1. In writing the set of domain I, we know that each element must be unique. Therefore, I will only include 1 0, which represents the 2 0 inputs in the set I. Thus, domain I is 1, 0, negative 1. Similar to domain I will only include 1 0 in range I. Therefore, range I is 0, 1, negative 1. Now, let's create an ellipse that represents the domain I and put all its elements in it. I will also create an ellipse that represents the range I and put all of its elements. Using arrow diagram and considering the ordered pairs in set I, 1 is mapped to 0, 0 is mapped to 1, negative 1 is mapped to 0, and 0 is mapped to negative 1. Let's check if set I is a function. Since we made sure that each element was unique in both domain and range, it satisfied the first condition. It also satisfied the second condition because elements of domain I and range I are subsets of set I. Now, it looks like the third condition is not met. Look, the element 0 of domain I was mapped to 2 elements in the range I. Remember, for set I to be a function, 0 must be mapped to 1 and only 1 element in range I. Therefore, set I is not a function, it is only a relation. Let's now have the third example. Let's determine if set G is a function. The ordered pairs in set G are negative 2, 4, negative 1, 1, 0, 4, 1, 1, and 2, 4. We know that the elements of domain G are negative 2, negative 1, 0, 1, and 2. Following the definition of set, the elements of range G are 4 and 1 only. Let's put all of the elements of domain G in an ellipse. We will do the same for the elements of range G. Now, negative 2 is mapped to 4, negative 1 is mapped to 1, 0 is mapped to 4, 1 is mapped to 1, and 2 is mapped to 4. Let's check. We are sure that the first two conditions are met. Since each element in domain G was mapped to one and only one element in range I, we are sure that the third condition was met. I would like to emphasize something in this example. This kind of example is confusing to most students I had before. Take a look at the elements of range G. Some students would conclude that set G is not a function because 4 was mapped to 3 elements in domain G, while 1 was mapped to 2 elements in domain G. However, the condition for every A, element of A, there exists a unique B, element of B, is true only for the domain. There is no condition in the definition of a function that states for each B, element of B, there exists a unique A, element of A. Therefore, we must be confident in our conclusion that set G is a function. Let's try the example number 4. There are instances that the set of ordered pairs will be determined from the predefined domain and codomain, just like here in our example number 4. This example also will help us understand more the difference between codomain and range. Set G is composed of the ordered pairs x, e, y, z, z, m, and w, a. Let's create the ellipse diagram. I will label the first ellipse as domain G with w, x, y, and z elements. I will label the second ellipse as codomain G with m, e, n, d, o, z, a as possible outputs. Let's do the mapping. Based from set G, x is mapped to e, y is mapped to z, z is mapped to m, and w is mapped to a. Is set G a function? Let's find out. I know you will agree with me if I say that conditions in 1 and 2 were met. Also, each element of domain G was mapped to one and only one element of codomain G, hence, condition 3 was met. Similar to the previous example, some students found this confusing. They thought that set G is not a function because there is no element in the domain G mapped to N, D, and O in codomain G. Again, the third condition, for every A element of A, there exists a unique B element of B, is only true for set A or the domain. Therefore, set G is definitely a function. Before we move to the last example, what have you observed from the codomain G? Brilliant! There are no inputs mapped to outputs N, D, and O in the codomain G. This is what we meant when we say the codomain is a set of possible outputs and range a set of outputs. In this example, the codomain is M, E, N, D, O, Z, and A, while the range is just M, E, Z, and A. Let's now have the last example. Let's determine if set O is a function given the domain O and codomain O. From the domain O and codomain O, set O was formed with ordered pairs such as pi, 0.4, 1/3, 0.8, and infinity, 0.1. Let's put the elements of the domain O in an ellipse and label it as domain O. Then, all elements of codomain O will be put in a separate ellipse and we will label it as codomain O. From the given ordered pairs of set O, I know that pi is mapped to 0.4, 1/3 is mapped to 0.8, and infinity is mapped to 0.1. We can obviously spot that there are no elements from the codomain O mapped to 1/2 and epsilon. Because of this, set O didn't satisfy the third condition that requires every element of domain to be mapped to one and only one element in the codomain. Therefore, set O is not a function. It is just a relation. Did you know that there are 3 classes of function, namely injective, surjective, and bijective? In determining whether a function is injective or surjective or bijective, we will shift our focus from set A or domain to set B or codomain. But how do they differ from one another? Is it possible that a set of ordered pairs has two classes? Let's find out. Let A and B be sets. A function from A to B denoted by f is a function from A to B is said to be injective or one-to-one function if for each B, element of B, there is at most one A, element of A, for which f of A equals B. The definition tells us that a set of ordered pairs must be a function first before determining if it is an injective function. Then, it is an injective function if and only if every element of the codomain or set B is mapped to at most one, meaning one or none element in the domain. Let's try our knowledge of injective function using our previous examples. Here's the example number 1. We know that set M is a function, but is it an injective function? Let's check if it satisfies the second condition. Condition number 2 says that each element of B must be mapped to at most one. Again, one or none, A element of A. In this condition, our focus will be the codomain. Let's cover the domain to see if each element in the codomain was mapped to at most one element in the domain. Yes, each of them seemed to map to at most one element in the domain. Since the two conditions were satisfied, set M is an injective function. Now let's have set I. Yes, I know. Since set I is just a relation and not a function, there is no point to know if it is an injective. Yes, because the first condition says that set I must be a function. Very clever, huh? Let's now move to set G. Set G satisfied the first condition that it should be a function before knowing it is an injective function. Now, since there were 3 elements mapped to 4 and 2 elements mapped to 1, set G didn't satisfy the second condition. Therefore, set G is not an injective function. Let's have the fourth example. Is set G an injective function? Since set G is a function and each element of the codomain is mapped to one or none element in the domain, it satisfied the two conditions. Therefore, set G is an injective function. Let's have the last example. Is set O an injective function? Similar to set I, set O is just a relation and not a function. Hence, there is no point of knowing its classification. The second classification of function is surjective. Let A and B be sets. A function from A to B denoted by f is a function from A to B is said to be surjective or onto if for each B, element of B, there exists A, element of A, for which f of A equals B. The definition requires us that all elements of the codomain must be mapped to at least one element of the domain. At least one would mean that it could be more than one, but it should never be none. Let's try the first example. Set M is a function and it is an injective function. Is it also a surjective function? Let's check for the second condition. To do this, Similar to what we previously did, we will cover the domain M because our focus now is the codomain. The second condition requires that all elements of range M must be mapped to at least one element of domain M. Let's see. Yes, all elements were mapped to elements in the domain. Therefore, set M is also a surjective function. Let's try set G. We knew that set G is a function, but it is not an injective function, right? Is it a surjective function? Let's see. There were 3 elements mapped to 4 and there were 2 elements mapped to 1. Obviously, it satisfied the second condition. Therefore, set G is a surjective function. Let's have the last example, set G. Set G is a function and it is also an injective function. Is it also a surjective function? Let's cover the domain G to see if it satisfies the second condition. It looks like it didn't satisfy the second condition because the elements N, D, and O of codomain G were not mapped to any element in domain G. Therefore, set G is a function, but it is just an injective function. The last classification of function is bijective function. Let A and B be sets. A function from A to B denoted by f is a function from A to B is said to be bijective or one-to-one correspondence if it is both injective and surjective. Let's see which among our previous examples is a bijective function. Since set M is both injective and surjective, set M is a bijective function. Let's have the second example, set G. Since set G is not an injective function, it is just a surjective function, therefore it is not a bijective function. Correct. Let's have the last example. Is set G a bijective function? We discover that set G is just an injective function and not a surjective function. Therefore, it is not a bijective function. To summarize our lesson, set M is a bijective function. Set I is not a function, it is just a relation. Set G is a surjective function. Set G is an injective function. And set O is not a function, just a relation. Did you find this video helpful? For more SEEKnaYan videos, please subscribe to my channel by clicking the subscribe button below and activating the notification bell. I'll see you all again in the next episode of SEEKnaYan. Problema sa SEEKnaYan, isik mo na yan kay Migo Mendoza.